Okay, here is an example for the optimum production quantity problem. Suppose we have annual demand of 10,000, setup cost, carrying cost, and daily production rate is 80 and demand rate is 60. So how many units should you produce, and how long will the production last, and what are the costs? Okay. So here is the computation, and let's go ahead and do these computations. Uh, let's do these computations in Excel. Okay, so demand is 10,000, cost of setup is 100, holding cost is 50 cents per unit per year, production rate is 80 and demand rate is 60, and unit cost is irrelevant at this point. Okay. And if we have the unit cost, then we can figure out what will be the dollar amount tied up in inventory, like we did in the OPQ formula. Okay. So now the formula here is, if it could be beneficial to set this up in pieces instead of having a long formula. We can set up intermediate numbers. So I'm going to insert a few lines here. Okay, so the formula here is okay. So let's set this up 1 minus d over p. Okay, so 1 minus d over p. Now this number has to be positive, and that would be if p is greater than d. If production rate is smaller than demand rate, then you will never be able to satisfy the demand, and so that becomes infeasible situation. And if p is equal to d, then you end up with 0, which means you have to keep on producing. If you stop producing, then you will run out of stock. So only when production rate is greater than the demand rate, this formula makes sense. So now square root of 2 times annual demand times the setup cost, okay, divided by, all right. So now we have to put a bracket here, C sub h times 1 minus d over p, all right, and then 1 bracket for square root. So then our economic production, optimum production quantity is 4,000. So let's compute some statistics from here. The length of production run is Q over P. That's our T. Length of production run per order is T, and that is Q over production rate. So that's that. So that will be in days then. So this is in days. So rate of inventory growth is what? P minus D. That will be per day. So that minus that will give you the rate at which inventory will grow. So now if you multiply these two, so this is the rate at which inventory grows per day, and this is how long the inventory will grow, the length of the production run. So that gives us the maximum inventory. So that divided by 2 will give you the average inventory. So we can use that to set up our holding cost. So number of setups per year would be demand rate divided by the production order quantity. Okay. Don't round this. This is average cost, average number. So you shouldn't round. So annual holding cost will be average inventory cost, average inventory times C sub H. Okay, annual ordering cost is the number of setups times cost for setup, one setup. Okay, well, they are equal. Okay, so that's what we expect. So annual unit cost, okay, we will ignore that. Okay, so that's 500. So let's go ahead and format all these costs. Okay. Now time between orders is what is the length of the inventory cycle from one order to the next. That's now we can express this in days because we have demand rate in days. So our order quantity is 4,000 and we will be using that at the rate of 60 per day. So that will be our time between orders. Now what is the percentage of time, total time? So this is the time between orders. What percentage of this time we'll spend producing, right? Production, percentage of production time. So production time, we already computed it to be that. So that divided by that will give you the percentage of time we'll be producing this product. Now often we want to keep the order quantity small and still be optimal. Okay, and this is the guiding principle for just-in-time management, just-in-time inventory. Suppose if you think that 4,000 is really large, we need to really bring it down to 2,000. So how can we do that? Okay, suppose Q star must be 2,000, right? All right. So and we want, one way of bringing this down is to bring down the C sub S value, the setup cost. If the setup cost goes up, that's when Q goes up. If setup cost goes down, then the Q will go, the economic order quantity, economic production quantity will go down. So that's what we need to do. We need to somehow try to decrease the setup cost. So how much should the setup cost be for 2,000 units to be optimal? So here we have to take this formula. Okay, so we take Q. So okay, what we need to do is to reverse this, figure out what C sub S will be. Okay, so square this Q, so that will remove the square root, and then you multiply Q with that and divide by 2 times D, that will give you C sub S. So first step is square that. Okay, and then we figure out that part which is that. So C sub H, which is here, times 1 minus D over P. C sub H times 1 minus D over P, which we already have right there. Okay, and then we multiply those two. Okay, now divide that by 2 times D. You have to make sure that the brackets are properly set up, otherwise you will end up with the wrong answers. Okay, so from 100 you have to bring down the setup cost to $25. Then you will be able to decrease your optimum production quantity from 4,000 to 2,000.